Hey, good morning, everybody, and welcome to our first lesson together in Chem 30. We're going to be going through Chapter 12, Enthalpy. So just to look back a little bit, we finished Chapter 11, all the enthalpy calculations, solving using units for enthalpy, molar enthalpy, mass, change in temperature, all of those variables. So you can review your notes on that. Hopefully you have been. We're flipping to Chapter 12 today, and Chapter 12 is actually really easiest one in the course. There's only 3 major lessons, and so we'll hit those in 3 days, and today is lesson 1. So on the screen you can see we've got the outcomes that you guys are going to be covering today. So at the end of this lesson you will understand what happens at the molecular level in order to have a successful chemical reaction. We're going to look at what activation energy is, and you guys are going to understand how activation energy affects the likelihood of a reaction occurring and how it really alters the success of a chemical reaction. You guys are going to look at the energy changes during a chemical reaction. So we kind of did this with potential energy diagrams, but now we're going to use some more vocabulary. Bonds breaking, bonds forming, and the changes in potential and kinetic energy that go with that. And finally, you guys are going to label some energy diagrams. These are a little different than potential energy diagrams, and you'll be able to use the terms reactants and products and enthalpy change and activation energy as we go through those. So let's rock and roll. Okay, so first outcome, you need to understand what it takes to have a successful collision. So our chemical reaction here is carbon monoxide reacting with nitrogen dioxide. So there's our 2 molecules. In theory, when they collide together, 1 oxygen will transfer and we'll get CO2 and nitrogen monoxide. And as you can see from the products, it didn't happen. So the question is, why not? What does it take to have a successful collision and create new products? So we'll scroll down. This is a successful collision. So there's 3 key variables to look at here. Number 1 is they collided. And number 2 is the orientation. We're trying to transfer this oxygen onto this carbon, and it will only happen if it lines up at the correct angle and, more importantly, with enough kinetic energy or speed to break this bond and make this bond, creating our new product, carbon dioxide and nitrogen monoxide, kicked off. So that's the key behind it. And now in your notes, you have some information to fill in. So we are on page 140, and the first one is, I'll try that again, 138. So first thing you need to do in your notes is just kind of make a sketch of this and point out that you need that correct orientation and speed to turn an ineffective collision into an effective collision. So those are our key variables. I'll pause for a second for you to do that, or you pause the video. Okay, so next we need to write down what are the key parts of a successful collision, and you've got space in your notes on page 138 to summarize these 5 key points that are all successful components of a chemical reaction. So I will get you to pause the video, add these to your notes, and then we'll move on. Okay, next section in your notes is 5 ways to increase the rate of a chemical reaction. They're listed right there. And I'm not really too worried about this guy. So really it's 4 that you need to do. And while you're copying these down, I have a joke for you that I'll put on the screen. Okay, can you tell me what those 4 things make? You ready for this? Sitting down? It's a catalyst. And adding a catalyst to a chemical reaction will definitely speed up the rate. Okay, so we're moving on to activation energy. So again, in your notes on page 138, if you pause the video, you can put down this definition for activation energy. And those of you who are auditory learners, activation energy is the energy barrier that must be overcome for a chemical reaction to occur. The entities must reach this energy or no reaction occurs. And we can add that energy in the forms of heat or light or electricity. All three work. So looking at this chemical reaction, you guys are used to potential energy diagrams, which we have right here. And on the left is an energy pathway diagram, which is pretty similar. It's got that same exothermic shape to it, but now we have added this bump, which is defined as the activation energy. So I would like you to copy down this diagram in your notes and label it. So we can pause the video to do that. Okay, so now we're going to talk about this reaction on the right because it is an interesting one. This is the thermite reaction, and in the thermite reaction, we take iron 3 oxide or rust, a very stable compound, and you can see it's stable because its enthalpy is negative 822.2 kilojoules. That's its enthalpy of formation, so that's pretty far down the energy hill of stability. And when it's reacted with aluminum, it forms aluminum oxide and liquid iron. Now you might be wondering, why the heck is it liquid? This reaction is so exothermic, its delta H is very negative. It releases enough energy to basically produce magma or molten iron. And you can see there's a big drop in enthalpy or potential energy to create that change. And we can calculate that value from the graph using Hess's law. The overall enthalpy is products minus reactants. So here's our products, negative 1669.8 kilojoules, minus our reactants, negative 822.2 kilojoules, and we get approximately 850. And that's exothermic, negative 850 kilojoules. And there is 1 mole, so the molar enthalpy is negative 850 kilojoules per mole. If you want to add any of that information to your graph, you can pause now. Okay, so now we're going to look at the same reaction with a little more information. We're going to do it as an energy pathway diagram. And as you can see from the diagram, this one has quite a bit of activation energy. When I do this one as a demonstration to get over the energy hill, I will either burn magnesium metal right inside the reaction to heat it up, or we'll use another reaction with glycerol and potassium permanganate. Both of those are hot exothermic reactions that add this energy to get the rust and the aluminum to slam together with enough speed, correct orientation to break bonds, make bonds, and then fall down the energy hill. And important to note on this exothermic reaction that the energy that we added, we got back, plus this additional negative 850 kilojoules, making it exothermic. And another way we could calculate that enthalpy change on this one is using their enthalpies of formation and Hess's law. Delta H is the enthalpy of products minus the, delta H, the enthalpy of reactants. And here's our enthalpy value. So I would like you to pause the video and calculate the exact enthalpy using Hess's law and the enthalpies of formation of both reactants and products. Pause now. Okay, this is a really cool video. So I would encourage you later on, or pause now and go look it up on YouTube. It's super exothermic. There's tons of examples of people doing this one on a small scale and a large scale. And as you can read here, it does have some practical benefits aside from all the exciting aesthetic benefits of watching this one happen. So now we're on to the last page in our notes, and we're going to look at the enthalpy changes in a carbon monoxide nitrogen dioxide reaction on page 139. So I'm going to you're going to pause the video, and I'm going to get you guys to label this diagram using all of this information that if we had a smartboard, we'd drag and drop it. So I want you guys to label it onto your diagram at the top of page 139. And while you've got this video paused, I'll be filling it in as well. Okay, so I've got my energy of activation. I've got my potential energy in kilojoules. And over here is my change in enthalpy. And according to this, it's negative 224.9 kilojoules. Is that enthalpy or molar enthalpy? Look at the units. Okay, my reactants are carbon monoxide plus nitrogen dioxide, and my products are CO2 and NO. And what else do I need to put on here? I think I've got everything covered. Energy of activation. Oh yeah, reaction coordinate at the bottom. And I could put the words activation energy to go with my symbol right there. This one is endo or exothermic. You decide. Okay, and one more thing to label. Again, in your notes, if you want to pause the video, you need to take these terms and add them to this diagram. And this is the exact same reaction in diagram form. So you can pause and label them in, and I'll start filling it in as well. So initially we have high kinetic energy with these two reactants in order to slam together. So we've got black is carbon, so that's carbon monoxide and nitrogen dioxide. This middle stage has very high potential energy because the molecules have slammed together with speed and created a very unstable, temporary activated complex. That's a key term in today's lesson. Okay, this is our unstable activated complex. It lasts for just a split second. If the orientation is correct, we can make a new bond, we can break this bond, and we have our new products being formed. And they leave with high kinetic energy and low potential energy, just the way they came in. And if we wanted to put this thing in chemical form, OCONO, one large molecule, and our two products are NO and CO2. I think I've used all the key terms there. Reactants and products. I sure hope your notes are neater than mine. Okay, we're almost done. So this part is just a review of that above example. So it says in the carbon monoxide nitrogen dioxide example, the energy initially absorbed to break the nitrogen oxygen bond is less than the energy released when the carbon oxygen bond forms. Repulsive forces push the products apart, converting potential energy to kinetic. Comparing the overall energy of reactants and products, we see that the have less energy, reactants or products. Then the reactants, resulting in an endo or exothermic reaction. So if I wanted to add energy pathway to this, I could put a bump like that and add my activation energy like that. Okay, so the last thing for you guys to do is answer this question in your notes for a energy pathway diagram for an endothermic reaction. We haven't looked at one of these yet. So what's it going to look like? You can pause the video and give it a try, and then I'll start labeling mine, and then we'll talk about your assignment. So a normal endothermic would look like this. To turn it into a pathway, I just need to smooth it out and add my energy of activation. So this has a very large energy of activation relative to the final position. Reactants, products, we are putting more energy in than we're getting out. So our delta H is positive, and in this case, it's positive 227.4 kilojoules. So for an endothermic reaction, more energy goes in than comes out. Okay, so here's where we started. Here's where we finished. Here is our delta H, okay, from reactants to products. Starting low, finishing high, and I think I've got everything. Oh, activated complex would be sitting right there, and energy of activation is this entire arrow. Okay, awesome. Thanks for staying with me. So here's your to-do list from today's lesson. And I've got two really cool online simulations for you to play with. They're FETs. One is called Reactions and Rates. The other is Reversible Reactions. I've got a separate little video that shows you how to manipulate some of the variables on these things, and you could spend 10 to 15 minutes playing with these, just trying every possible option and becoming an expert. I've got all that listed there. Go to YouTube and watch a thermite video. Very cool. And then finally, some super exciting textbook questions for you to do that cover 12.1. Tomorrow will be 12.2, and then the next day we'll do 12.3, and then we are done chapter 12. Okay, have fun and chat soon.